My topic today is a very interesting one. I come from a background of running and liaising around with data center operational teams. So this is a good topic for in today's era of public cloud adoption and the degree of abstraction we have today. I think this topic is going to be very insightful and you're going to learn a bunch of cool technologies. So how do I hit next? Cool. So my name is Srivatsa. Currently, I'm an SRE at 1 to N, and we're solving great problems at scale here. My interests are big time into military tech. I'm a fighter jet fanboy. If you guys are also into military tech, hit me up. I write on the same, and I also play the piano. So today's topics are going to be pretty, straightforward, but also insightful for us to learn. So my goal is pretty much one thing here today: introduce you to this concept and make you realize that this tech exists, right? We're not going to be going into implementation level details or going into very nitty gritty. We just want to establish that this is what makes X makes Y possible, right? So let's go from this, and I think I have to run you through this because it's important and it'll stay in our head. So I'll help you first form a mental model of what a data center look like in today's world. Then we'll also go into insights into what systems and software technologies go into building one. Then we'll chalk up a mental model of a data center ourselves, okay? And then we'll become an infrastructure as service provider first, then we'll become a platform as service provider next, here only. Then I'll show you two cool technologies that run data centers and power the very resiliency that you see today. These are the bedrock technologies, and then we'll, of course, conclude for lunch. So this is your mental model of a data center today. Yeah, nobody likes to touch hardware. People treat hardware as the holy grail, and then if you touch it, you end up in that mess. Probably you're not even seeing him cry under the bunch of wires that are there. But no, yeah, seriously, this should be your mental model of what a data center looks like. It's NCS, right? Network, compute, storage. Data centers are elementary building blocks. You scale in units of network, compute, and storage, okay? And then you have P and auxiliaries, which is just power and auxiliaries. Think of everything else as an equipment in the site that supports your NCS, okay? This is a very good way to think. Also, when you in system design or anything, when somebody asks you, you can approach the problems with NCS. How will you solve for network, compute, and storage? Addresses a lot of things ahead of time. So let us start with what actually is going into data centers these days. You have servers, of course, you have thousands of servers. It starts with virtualization, right? So what is virtualization? We've addressed this problem where olden times, each employee used to be given a server, or each application used to be running on a particular server. It had scaling problems, whatnot, and then people wanted to scale more efficiently with a single hardware. So the hypervisor was born, basically, which is leveraging virtualization. So we can see, while this remains the conceptual implementation of that, the industry operates at two types of hypervisors, right? So while we now explained what is a hypervisor, it's just a software that allows you to run multiple virtual machines on a single physical machine. We have type 1 and type 2. I'm sure all of us have used a combination of these as developers, operation experts. Type 2 are usually mostly used for your local development setups. You use things like VirtualBox and whatnot. Type 1 is where the industry plays at. There are players like Nutanix, VMware, KVM, all these guys. Bunch of open source and bunch of proprietary guys. So in type 1, as we can see, funda is very simple. You buy hardware, flash hypervisor, run workloads, okay, time to market and whatnot. Pretty standardized. People know what to do. In type 2, there is not much enterprise or usage of business. It's for your interaction. Basically, you can't run major workloads on that. Cool. So now how did we get here? Let's think of this. So the purpose of this slide is to introduce you to the three different types of current hardware architectures that exist, and after this we'll take a break. I'll take a break to just understand that if you guys have gotten the gist of it, right? So traditionally, when data centers are racked, how many of you guys know what a rack is? Right? So can anybody name like how tall are racks, or what is the unit of measurement in a rack?
It's basically the number of
no, not CPUs.
servers.
Yeah, so
basically how many servers can be stacked?
Yep. So we've all heard the term called rack servers, right? So rack servers are nothing but a rack itself. The name comes from the rack. So racks ship in different configurations. Many, like if you have a big data centers, they usually stack it to 42 or 48 U rack servers. Now, what used to happen there is in olden times, there used to be 3-tier architectures. Okay, it didn't start from software, 3-tier. 3-tier actually was the limitation of a hardware that people started describing into a software abstraction, right? So traditionally, what did you have? You had storage. And then you had a network switch for that, and you had a fiber channel switch for that. Network was to, for your traffic, and then you had a fiber channel switch, which is again a switch, network switch itself, meant for storage traffic. You had to link them up, and this was all done just to talk to your server to storage. Okay, so what this meant, all of your SAN and NAS over the wire, storage over the wire concepts were implemented here. Then things got better. People said that, hey, like fiber channel switch be switchy, we will converge that.
I know the network switches. What's a fiber channel switch?
Fiber channel switch is basically a dedicated traffic path to route storage traffic, right? So you have a data plane and a control plane of sorts, right? Like traffic. Yeah, mostly that. So if you're trying to write traffic into your hard disk, it will go through here. You're trying to route traffic outside, it will go somewhere for another switch.
Basically, it is packets flowing, but for a dedicated.
Yes. Storage purpose, non-storage purpose. We can classify it like that. So converged is what the world runs on today if you are not running hyperconverged, right? So I'm trying to do this to introduce you guys to the term between converged and hyperconverged. Now, the keyword of hyperconverged is going to take a lot of importance in the upcoming slides. So before that, I'd just like to say, 20 years ago, right, what we're talking now was the norm. Everybody's like, abhi yaar, virtualization hi kar raha hai na, matlab, we are there. What is the fancy things? But today it's exciting for us because we're in a realm of public cloud and a mix of things. Like the minute you grow into a little bit of expertise into your public cloud domain, you start hitting these core problems like of networking, storage and stuff, and then that actually kind of brings you down. You have to understand how the underlying technology is implemented. So yeah, I think I'll take a pause here. All of you are on board with me, right?
Actually, if once can go over the difference between network switch and fiber channel switch, that would be great.
Cool. So see, network switch is basically if you see a server, if it has to think of your, what do you say? Well, let us just think of one server, right? It has its own storage. Now, if it has to interact with the outer world, and if you're using laptop as an analog, it's just going through your router and exiting out. But if you have a dedicated storage, which is provisioned for you in like a hard disk, a bunch of hard disks, you have to establish a certain network for that. That's called the storage network. And all your network packets, sorry, not network packets, your storage data is flowing through that. Basically, it's meant only for a storage path, a data path. Hotline, yes. So when they say storage, SAN and NAS, right, network attached storage attached network, where your storage is flowing in remotely. This is what they're talking about in a traditional way. I have a photo. I'll show you that.
Okay, when you say fiber channel switch, it is actually an optical fiber.
Yes, yeah, it's a 10G, 25 gig, whatever, like fiber channel.
Server and the storage.
Yes, correct. That is how it is.
Okay, so it's basically like those premium launches you have in your phone.
Yeah, dedicated. I will only talk to this guy over this channel. Nobody else disrupt my bandwidth. The goal of this is to utilize full bandwidth for only storage. If you're running things in mix, you conflict usually.
ATC radio frequency.
So that's what it is. But the hyperconverged is something of a recent trend that is picking up with limited players. And of late, Nutanix is probably one of the top players in hyperconverged infrastructure. And we'll take a look at how they're actually building on this, right?
Okay, can it go back?
Sure.
When you talk about converged, then like how is it different in hyperconverged? Like when it's storage and server, so are you like, is it like something similar to what Saurabh said, that you're basically trying to combine the storage and server together?
Yes. So what happens is, for example, then you have your storage and HBA cards which take on the dedicated traffic. It's built into the server, but they are routing storage traffic, and you have a logical separation at that point. The hardware is going to handle it for you. But what's going to happen is you no longer have to segregate your dedicated network switch for traffic and dedicated network switch for storage. It has, the ports are in the same box basically.
So it's basically your personal computers into the data centers.
Kind of thing. It's a bit different. Let me go through the slides and
Is analogous
of what?
like for example, my PC or laptop has got my own hard disk storage,
Hmm.
and if I'm going to have use it as a server, nobody can stop me.
Huh.
Right?
Same thing. So you are at one place basically.
Okay. And here, when you say one place, is it like physically one place or like
Physically. So in converged physical is it's in one box itself. The good thing is a laptop. Okay, but when you think of these Synology and stuff, right? You have your SAN solutions, terabytes of hard disk stacked upon. You can access it over network. That can give you a storage of like remote storage. Basically, you're accessing things over the wire. Now in data centers, the wire and this thing's location is the same place, basically.
But, okay, so we are basically talking about on-prem stuff only.
On-prem, yeah, very solid on-prem. Data is in the same location as the compute. Okay, but it's just that different racks are there and they're wired up. So this should explain more in terms of when we say taking up. So I want you to read this left to right, right? So
I have one question. Like it will limit actually the use of hyperconvergence, right? Because I think then means it will change so many things. Like when you have a server at different place and storage at different place. Okay. Then you can manage who else need how much server and the storage like as per their need, and then you just need this network switch.
yes.
But when it comes to hyperconverged, then it means it's specifically exactly made for that problem or the company or so.
No, not really. So this I'll show you where the advantage for hypervisors come in. Hyperconverged hypervisors come in. So this was a traditional three-tier architecture that used to run data centers for a long time. Now, if you think of it from an operational perspective, right? There were storage providers like you have NetApp and stuff. You have NetApp. These days, you have a bunch of guys, older NetApp, Cisco, UCS, all those guys. They used to run their own interfaces, their own equipment. So the operational teams had to be storage experts, virtualization experts, and also they had to have a knowledge of how to hook these things up. And what this meant in the lifecycle management was hardwares were different, managing their life cycles were different, which meant that if this new versions came into storage, you would have to induce certain form of like careful maintenance and very different things, like a lot of operational overhead for maintenance. But what Hyperconverge ended up doing was it introduces a software layer which enables you to think less about all of this, and because all of this is at the same box, you're doing things at a faster speed. If I have to add capacity tomorrow, all I have to add is one box. I don't have to think about working with like 3 different components basically. So if you read this from say left to right, you can take a look. Before, this is what we had a little bit of fiber channel switching off and switch setup here, and then that moved into a hyper converged setup. And if you see here, each of this unit is now a self-contained entity of storage, network, CPU, memory, which is our NCS model. Network, compute, and storage is now into a singular unit, and all of them runs through one network. And that is the purpose of HCI here. You converge the entire data center stack, what we mentioned. You converge compute, storage networking, and then virtualization. So the legacy recall, what I wanted to mention here is for people who worked in these things, you would always remember things of how this section, fiber channel setups were set up. You had to daisy chain. There were storage controllers, there were storage arrays, there were also ID racks, which were remote access controllers. You had to log into each of those things and check out what was happening. All of that got abstracted. So what I mean to say here is basically this. I've got a blur photo, for example. This is your rack today. So these were your storage arrays, and look at how much space they're taking up basically. And then you have a one server here, then you have your network switches here, effectively eating up networks rack. But when the time came for hyperconverged, each unit there is capable of performing those 3 functions independently. So the more you grow them, the more you're scaling this capability. Okay, so this looks very clean, this is maintainable, and this is also picking up at a rapid pace, especially after this Broadcom acquisition of VMware, right? People are moving towards Nutanix a lot. So
I have a question on that. Can you show the last one? So as you show here that there is a switch and it is taking up a lot of space. But do we require a torch switch in these racks?
yes. So in Nutanix,
how would they communicate with each other, all the different individual
correct.
racks?
So each rack obviously has a Tor switch. Tor switch, for those we know, is top of the rack switch. So here we had multiple equipment here. Here in the case of Nutanix, you can stack all Nutanix all servers, for example, and you can have one Tor switch on top. And as each rack gets its own Tor switch, you can then cluster them up basically. So one server here will be connected to two switches for active, standby, active, active. So that is how it runs up. But effectively, you're saving space. You're throwing both memory, storage, and compute in one rack, effectively utilizing your rack space way better than what the 3-tier would have done, right? So this is hyperconvergence in play.
One question.
Huh.
If a component fails, then I would end up replacing the entire CPU memory.
No. That is very granular, which is a good question here, because we are here at that stack. So as I told you, this is what an elementary unit of a hyperconverged architecture looks like at this point. So you can see that in one server that I bring or stack, I can have my combination of SSDs and HDDs, and then I can have and then you have a software SCSI controller on top of which the hypervisor runs, and you have compute and memory at the same place. Now what does this do? Each node in a cluster is converging, right? Hyperconverging, right? So you have achieved data locality. Your workloads are reading from the same storage in the same hardware. Okay, now this changes things in terms of performance. You're no longer reading over the wire. You're no longer reading from a little bit offshoot storage. You're reading literally from where you're writing, and it's great. It's great to have that performance advantage. So we are doing that while we are effectively reducing our rack space. We are keeping the same punch per rack. Okay, in fact more, you can say. So at scale, I've seen this run and scale to almost 800 servers back at our organization with around 15,000 VMs running over this, and we have clustered this. So while this remains an individual unit, when you bring things together, it gets clustered. So which is our next slide. iSCSI is your storage driver basically. So this is what happens when you cluster these things together. You saw those racks, right? You can cluster X number of things to become a cluster of a Nutanix. And now if you see, effectively at this point you become a distributed systems, right? And distributed systems have three principles. Because you're running at data center scale, you should not have a single point of failure. You should not have any bottlenecks at any scale, which means you must be linearly scalable. And then you should leverage concurrency for reads and writes, which means you should have built-in good tolerance for implementing things like compression, deduplication, replication. You should have support for that. So now when this is happening, here's the fun part, right? When you're a hypervisor and you're scheduling workloads, the user VMs running here are directly interacting with the data in the same unit of server, which makes performance faster. The user VMs running on this, perhaps in the same cluster, they're utilizing the same storage here, and the same thing for that. So when you bring data closer to compute, you have an advantage. And now that you're a distributed systems, at this point you're also implementing things like replication, fault tolerance. So you have your data segments available in different servers as well. So you have now established rebuild capacity. Now what we will do with that is I will tell you. Okay, wait, 1 second. When you cluster so much of these things, right, this is where the power of software defined features come in. So what software defined does is you bring in things like virtual networking, your virtual storage drivers, and your workload schedulers. These are all software additions to hardware to make them super powerful. And what I mean by that is, in this architecture, if you see, when we cluster so many of these servers together, right, you're no longer dependent on the hardware's ability to do something. When we are implementing software defined stuff, if you want tomorrow, for example, we already have replication, we are replicating within the cluster, we have compression, deduplication. Tomorrow you're asking for encoding. I don't have to think too much about hardware. Like, hey, that's a software update for us. Wait for the next version, we'll just push it in. And the good thing about running SDNs, software defined stuff, is every hypervisor today is almost supporting that, right? So you have VMware, Nutanix, Hyper-V, all of them support virtual or software defined architectures. So in the same thing, tomorrow we currently have say interface adapters for storage. We have SCSI, NFS, SMB. Tomorrow somebody requires HDFS. Yes, the team can take that up and say that, hey, next version, same software, next version of the same software, we will bring you this support. And I'll tell you why this is a good advantage. It's because hardware is eternally expensive. You cannot, to buy one feature, you cannot switch hardware. Okay, so this is one thing. Now benefits, right? These are the core benefits. Basically, you're not relying on any custom hardware capabilities. You can develop and deploy these features through new simpler software updates. This means that your deployment, the new feature just needs to be brought in by an upgrade. And what this means is businesses no longer have to worry about an array of decisions. They just have to ask the data center team, hey, when are we upgrading? What version are we on? Okay, and this also improves in terms of vulnerability management, security patches, everything. There is a life cycle management.
Yeah, so I had a question. What's the compute overhead of this software-defined like driver solution compared to like directly accessing the net storage drives, for example? Like, is there a performance loss?
No, there is no performance loss. In fact, because like these guys have dedicated, what do you say, storage access drivers, right? So the iSCSI just does that. iSCSI is your storage path into your hardware, and because that runs on every node and that node clusters up, your storage performance increases per se. So you're running things reads at hot tier at like almost near ends of nanoseconds and lower ends of milliseconds. And if you're running it over the wire, like one node wants to access another nodes, it's always in millisecond read, sub 5 millisecond read times. So, and this also means that up to a point of your hardware, you can be running 3-year-old hardware and not buy new one, but still if you're compatible with that hardware stack, you can just upgrade it. And open source has a lot of contributions to do here. When we say networking, right, when we say that we're virtually networking a bunch of these servers, there is this open OVS. Have you guys heard of OVS? So this is Open Virtual Switch. It's a great project. Then we have virtualization. We have KMU, KVM, always open source. Then storage, we have projects like Ceph. It's actually a culmination of these projects coming together and like forming some proprietary kind of a layer that these major private players are exploiting. Okay.
So a few years back there was this project called OpenStack. Does the industry use that, or is it optional?
I mean, adoption rates are questionable. Depends on the friendliness of the stack provider, right? Like so, Nutanix has laser focus on customer service, for example, and because of OpenStack, like and being community driven, maybe the adoption rate and confidence at enterprises level might not be that great. But yeah, there is definitely a market. Okay, so I am not sure of the latest adoption rates. We can check that out later. So this is one thing, and this is what the scaling with scaling efficiently with hyperconverged stack gets you. So the fun part about this is the number of increase in nodes is directly proportional to your performance capacity and performance and recovery abilities. Okay, because you're scaling say metadata and stuff, the more number of nodes you have, the less number of metadata distribution takes place, but effectively you are maintaining rebuild capacity. So even at the loss of a node, the number of things to fetch per node becomes less, and the performance also improves because each node is now performing a good decent level of acceptable number of workload duties, and you can push that to its limit. So the same thing with capacity, of course, and you can see some of the configuration maximums taken from one vendor. You can scale to a maximum of 32 nodes per cluster, and per memory per VM scheduled you can do up to 4.5 TB. Okay, and also per disk size can go 64 TB per VM. Right now, this is virtual disks actually. So in SCSI you can do storage blocks, which are the equivalent of LUNs. Right, so LUNs can scale bigger than that. Basically, you can attach a LUN block, so within the software. So this is something, and this is a cool part. Right, now that we are here at a point where we understand how we are trying to stack up our data center, we have an enterprise DC. Okay, I'm telling you that you have say 500 servers at your disposal. How do you decide how to set up, right? So at an enterprise scale, this is what I have seen. What I have seen, we divide per data center into an environment basis of sorts, right? Where we take up say maybe 3 clusters for general purpose usage. Now these are for running your application workloads, fine, koi app server, web servers, whatnot. Then you take up say maybe 2 clusters which are storage optimized, and then you take them up for your on-premise hosted stuff. If you're hosting on-premise Prometheus, InfluxDB, whatnot, everything storage heavy can go into storage optimized clusters. And then you have compute optimized clusters. These are for your compute sensitive workloads. And the reason, I think somebody asked, right, if you're scaling, wouldn't you be scaling with full capabilities? The good thing about this is in Hyperconverged, you have dedicated nodes. You have a general purpose node, which brings the entire army with it. It brings storage, compute network. Or think of this way, in Oracle environments, right? Oracle is very licensing sensitive, right? They do billing per core. So I cannot randomly keep adding nodes and be like, I have X number of nodes. You are very compute. So you will take a compute only node, saying that my Oracle will run on compute only nodes, while the data it resides in storage only nodes. We have the power to segregate compute, storage, and network, even while remaining in the hyperconverged infrastructure architecture. So per data center, maybe this, and then obviously there is always people who are running business fronts, so you have Microsoft dedicated clusters. And the fun part about this, in maturity of OEM providers compared to open source, right, for what you're asking, you have full API driven provisioning. Like these guys have provided us API to interact with these systems at a very granular level. You want to provision a VM, you want to provision storage blocks, which can mean file, block, or object storage. It gives you native alerting endpoints, and also SNMP integrators, because at hardware level you cannot these are very high performance systems. You cannot add monitoring agents and stuff inside there. It would absolutely hinder stuff. And then you cater for failure modes. Obviously you're running enterprise data centers, so you have to cater for failure modes. So now let us start for the smallest failure mode, which is a disk level failure, right? As I told you, I have a slide for that. So we have disk level failures, which is handled by your metadata distribution. Each content is based on technologies like copy on write and stuff to ensure that you always have X number of copies available across the cluster. At node level, we again have fault tolerance, which is the system, because you're this big now, has distributed enough metadata and data by replication and deduplication, that you can afford to lose a node completely in your cluster. And then we also have solutions that we have to cater for if we lose an entire cluster. What if you lose an entire cluster, right? So then the business demands this for you. There are some businesses which are very regulatory heavy, some businesses which are very performance heavy. So they are like, I cannot afford you, so I cannot let you do this without maybe saying that give me a live architecture, give me a two-side thing where either I need guarantee of you being live in both sides, or I need you guarantee that if I fail here, I will take over here. Things like that. With disaster recovery capability, basically. So,
Two questions. First, the first 2 points, they sound a lot like how we use USD. So, is that the correct analogy that I can?
The which point?
The first point, per data center environments, it sounds like what AWS does for us.
In terms of offering EC2 and all, like there are.
Oh yeah, correct, yeah, exactly. So you have your T2 micro and you have storage offering things, right? So this is a good point. My next slide is covering onto that. Okay. So because you have like how you have workload optimized entities being available to you for provisioning, same thing is this is good. We are currently building up that capability, and in the next slide we'll see how we become that IaaS provider, right? I'll show you in that.
Okay.
So
point is about cap theory. So cap consists of availability and partitioning. So you need to, you can only have two and one is going to be compromised. So how do we handle that?
So this is in terms of these are mostly CA systems, okay? Because at this scale, partition tolerance becomes a what do you say? How you have fail safes for partition tolerance, but naturally when they're functioning, they're generally consistent and available. The focus is there.
We are talking about one data center. So let's just talk in AWS analogy, because most of the people know that. And an availability zone has multiple data centers. Okay? Multiple availability zones makes up a region. Multiple region makes a global network. So we are just talking about the one data center inside one availability.
Yes.
Yes. So now the network partition is based on geography there.
Correct.
AWS.
Yes.
So these are CA systems, and when you talk about AWS as a whole global entity, that works on CAP also.
Okay, I'm not sure of what do you say, AWS like terminology on relativeness like that. But what I'm trying to say is, if you are having two data centers or two data centers within like the same country,
Yeah.
okay, most of them we are doing it like that way. Unless AWS has the provision. It depends on the business where your data centers are. Okay, so this is when we say cluster level tolerance, and I say that I have to cater for data disaster recovery. I have to ensure the connectivity.
I think if we give analogy to the AWS, it won't work because the business case for both the type of system are different. For hyperconvergence, it is different, and for AWS, it's different. Saying this, it is what makes AWS possible.
Yes, so
That is why I think the analogy would not be great. Because if we will take this system in AWS, I think the cost will shoot up.
Yeah. No, the thing is here, here the, what do you say, most of these things, right, live architecture or inter data center things, you have companies like InfiniBand and all of those, right, those are providing you 100 gig level bandwidths, right, like you can't provision them on AWS without coming off the radar. So this is basically the foundational structures of data centers itself. Right, so we're talking about that. So if given a data center, what capability should you have? I should have the capability of being live, or I should have the capability of being on active standby, right? So you can multiply that in concept. So, okay, I'll stop here. Again, just to ask if all of us are on board, right? We're on the way to build our data center and structure it right now. So now that you have your bunch of servers, you have workloads running on them, there are interesting ways in which people do capacity planning in a data center. Okay, one way is that majority of enterprise workloads, right, they run virtual machines at the behest. Okay, containerization is slowly coming in, for which support is also being built into these systems. So when we say capacity planning, right, what is our major requirement? I should have the ability in my such huge infrastructure to drive the placement of workloads effectively across clusters. We have segregated our clusters, right? So given a requirement, tomorrow somebody asks, give me a virtual machine for this. You should know on what logic, on what conditionals are you provisioning it, and in which system, and what capability that provisioned entity should have. So the same thing. In a cluster, there are three main things. Again, it is coming down to compute, memory, storage, right? So you can see in CPU, the fun part is one server comes with 56 cores, 2 socket, physical, right? And we know in virtualization that gets enabled by virtual, what do you say? So you go into vCPUs. So vCPUs is effectively a double standard of that. So 56 becomes 112, and then you have into 2 basically. Your 56 core per socket, you have double, you get your vCPUs. What we monitor here is total versus provisioned. Okay, either one of these things will top off in your cluster, giving you a amber or a red alert saying I'm running out of CPU, running out of memory, running out of storage. Now the fun part in AWS is we're also used to auto scaling and like leaving things to fate of whatever the reservations and all of those things. But the fun part in data centers is you cannot scale infinitely. So you have to be a lot more factored into what capacity you have already put into these machines. The idea of start small, grow big later during expansion can be costly in data centers. So there are a little bit of math heavy calculations. These are very just high level stuff that we're talking about. If either one of these exceeds, say 70% is my threshold I have kept, I will order new kit directly. And what ordering new kit means is that I have to bring my new hardware, and in the hardware world, ordering new kit means minimum of 1 month. Okay, which means I should know what my capacity might blow up into 1 month from now. Which also means I can't, if I am not in a position to do these math calculations correctly, I should operate with headroom, which is what many people do. They don't calculate point wise and say that I have X% capacity for next month. They will say, sir, 30% headroom hai, we can take. Okay, and then once we take that, we order new kit. Okay, and also the good thing about data centers is because you age with time, servers also age with time. So servers get decommissioned every 3 years, 2 years, depending on your company policy. New servers keep coming up, and then based on the new capability, you expand their storage, memory, whatnot, right? So these are what you do. And the two good things is actually the ratios here. These are what Grafana dashboards for infrastructure people running, say, hardware like this are built on. We have something called as CPU cores to VM ratio. In the available of total versus provision, if I calculate this ratio, which is number of cores to number of VMs, what do I get? If the ratio is going higher, I know that I am in a position to allocate more vCPUs to VMs, which is a good thing. If this, so the more this number it is, the better for you. But it comes at a cost because you're paying for those. Next is VMs to host ratio. Now, if there is a lot contention, if more. So this condition is more the better, it's great. Per VM, I am in a position to allocate more vCPUs. But the number of VM to host ratio again takes a hit because one hypervisor is now suddenly hosting a lot of VMs. This is like your VPS, shared VPS. So they will tell you before hosting itself. They will like, bhai, if you are running a noisy neighbor problem, this will impact you. So these are things we have to keep in mind. Now this depends again on data center to data center, business to business use case. There are numbers which businesses arrive on. They say that this ratio is acceptable for us. This is usually talked in the context of we should always maintain X ratio. And VM to host ratio, they always set thresholds saying that if the number of VMs per host cross this number, maybe add a new node, redistribute the VMs across those nodes so that it's being served better. Okay, because VMs are first class citizens of hypervisors. They have to be treated with priority, right? So now think of this. You have enough things. We know what the hardware looks like. We've set it up on a data center. We know certain metrics to monitor on. Effectively, you are now taken shape of yourselves as an infrastructure, as a service provider. Okay, so now if you want to build on these things, right, if you want to build a provisioner, you can have your custom scripts now. As I told you, these things are API driven. You write your own logic to create an endpoint, to create a VM, an endpoint to create a storage volume. You build this, and based on your metrics, these are some key metrics on which you can build your builder logic, right? So based on these logic, you can tag your clusters open for build or closed for builds, which is live or full. And then the one way we used to do it is we had a big Grafana dashboard full of tables with all our clusters, and against that we could see at any given point of time per region how many clusters were available for build and how many were closed. And if they were closed, which means they're running, they're serving production, but they're at capacity, so no more scheduling of workloads on that, right? So this is something which is very interesting. And next thing is monitoring, right? As I told you, it's pretty fun. At hardware level, the day you install your server on the rack, you don't get Grafana out of the box. Okay, it's not as easy as saying, "Arey, server pe node exporter laga do." You cannot do that. Okay, so at the hardware level, when you plug in one server, right, the capability they give you is something called as ID racks. This is a Dell specific term, but the generic term is RAC, remote access controllers. Okay, this is a fun piece of technology, you know. So even if the server is powered off, IDRAC will stay functional because IDRAC has a dedicated port on the server and it is interfaced with the rack of your data center. It's not interfaced with the server or its neighboring server. So if the IDRAC is functional and available over a network, a bunch of these servers when clustered can have their own VLAN called as out-of-band network. Out-of-band networks are not, they don't interfere with production networks. These are things for management. So if I want to remotely power on a server, if I want to do fleet management, basically when I have 800 servers, I will do fleet management. IDRAC is your best friend. So at the bare minimum, getting power consumption details, getting heating details, getting what the battery status looks like, all of that happens at IDRAC. Once that matures, you people leverage that IDRAC APIs. And we have one person from VMware who's also worked with them, which is a great thing actually. That was good recall. And at hypervisor level, what happens? This goes into OEM provided. Okay, Amazon used to run, say for example, Zen servers, so they would have their own monitoring backend for that. VMware, Nutanix provide good out-of-the-box dashboards to monitor right outside the box, and they also provide APIs because obviously people, you know, fancy these dashboards in Grafana and stuff. So they're like, you give me the API, I will do my logic on this. And then workload level, which is basically those custom metrics I told you about. They're all extracted from the APIs provided by the OEM vendors. You build your logic on that, build that logic of ratios and whatnot, set it up, leave it. After this, rest of your melt stack, once your workload is running, right, things kick off here for your applications, right? So then you can do your all of the metrics logging. So yeah, you're pretty much an IaaS provider now, right? You are able to, similar to AWS, you are able to publish your offerings to your upstream. Who is your upstream? The platform team. Now you are able to, provision virtual machines, containers, and EUC. EUC are things like Citrix, VDI, and all of that. Okay, you're able to provision small instances of that as well. Now you're also in a position to provision block, file, and object storage. You're also compliant with security, network related services by having those DR things in place, whatnot. Now, this is a private cloud in an enterprise. The consumer journey for this infrastructure starts from here. So the platform team kicks in now and they'll be like, how do I consume your resources, man? You're saying you have thousands of CPUs, thousands of GBs of RAM and terabytes of storage. How do I consume? You then ask them, use my APIs, whatnot. You publish your offering, riding on that infra, the platform team publishes offering to its upstream. They're like, hey devs, we've got the infra now. If you want something, tell us. So teams start to form. You have a data services team. They're like, you want warehouse, I'll get storage. You want databases, I'll give you. Backup services, I'll give you. Then you have, again, platform services, things like your self-hosted GitLab, Artifactory, what right now, in-house tooling things, CMDBs, which are your big dumps of configuration wherever they are. XYZ services. They're all reliant on that one solid piece of infrastructure that you have built. Cool. So this is a good journey of how you can understand once infrastructure is set up. Within the company, there are degrees of consumers. And you being an infrastructure engineer, become the first level of provider at that point via software. So these are some cool things. How many of you worked in the virtualization domain here? I'd like to ask. How many of you have dealt with VMs like Bear, like KVM good points? Have you? On? Long time ago. Okay. Anybody else who's flashed a KVM and said that इसपे मैं VM बनाऊंगा?
I remember the day when my college server I worked with not KVM.
Got it. So as we see, I think the trend is mostly that you are all consumers of virtual machines. We didn't have, say, maybe the insight or opportunity to say that, hey, what if I'm getting a virtual machine? Have you ever wondered, like, who's giving me this virtual machine? Like, where are those EC2s coming from in Amazon? Like, how am I able to get 1,000 EC2s? Where are they coming from? Who are they managing? What if my current running EC2 goes down? And the fun part is your EC2 might have gone down and you wouldn't have realized it because the failovers are so efficient. Okay, or the VM that is running on the hypervisor hypervisor might have gotten stressed out. Again, you wouldn't have found out. Why? It's because of this first cool technology that we are going to implement. It's called VM live migrations. So a brief introduction to that is, a VM live migration is the ability of a running virtual machine on a hypervisor consuming resources to live migrate onto another hypervisor without disrupting user experience. Okay, so internally a lot of QoS like things kick in here. Okay, you have to ensure that, because if you're running a chat application and I migrate your application running on that VM, you should not be the affected victim. This technology enables that. Okay, so why we have this capability is mostly to address things like, network is unreliable, it's a thing. Okay, so you have to cater for things like flapping network cards. You also have to cater for power supply issues. Okay, then network unreachability issues caused due to other events. Then hotspot issues on the nodes. Hotspot is basically what I told you. If you have noisy neighbor and your there's a consumer A on the hypervisor, consumer B on the hypervisor. Consumer A is noisy and consumer B complains to you saying that I don't want to run next to this guy. Can you please take care of this? What do you say? Hey, you can't say that wait for me to scale my hypervisor. It will get better. You will be like, okay, I'll migrate you. Tuck. It's a button click on this platform. Actually, you click the VM and be like, bro, you move to this VM. So this is the technology that makes that happen. Okay, so this almost enters state machines kind of area. I am not too proficient at that. But if we talk about this in stages, basically, there is a listener on the virtual machine. It listens to tasks and then it works with the scheduler. Okay, it listens to tasks of what kind? It says if this particular host is unreachable, if this particular host is experiencing network flapping, there are all checks built into that. If any one of these tick off for a X period of sustained time, kick off my migration. I don't want to take chances because this host might be on an imminent edge of failing or it's showing signs. For example, when you guys do heartbeat checks, these are clustered applications, right? There's heartbeat checks going around. So one small check to trigger a migration like this could be that if my neighbor is unresponsive for the next 15 pings, evict all the VMs running on that. Let us not take a chance, because if it fails, right, the cost of those VMs going down or being restarted on another node is higher. So you take a proactive step and then you migrate these VMs. So it is nothing but the task comes into the VM where the hypervisor knows that this VM is now tagged to be relocated. So what happens? A target VM is set up on the neighbor node. That is basically a shell virtual machine. Okay, and then what happens? There is a the cluster slowly starts to migrate its memory into that. Basically, point in time, it keeps replicating. Like, okay, I got something, I'm moving. Got something, moving. Got something, moving. Now what happens? At one point, you can see this state of paused. This will keep happening. Which is basically on the source, the VM is live, doing its work. But on the target, there is a new VM getting ready, receiving its state, okay, periodically, and this happens within milliseconds, it's receiving state. And then what happens, which is, when I say state, it's basically memory, in memory. So it's like ultra fast snapshots. And then at one point where we are having to cut over, there is a pause, okay. This is where the quality of your hardware and everything comes into picture. That pause has to be so small that your sessions, timeouts, TTLs have to be effectively catered for and moved into your target machine. And then the target machine has to receive the target machine. What happens, right? The fun part is it will come up without having received the entire state, because in memory there are something called dirty pages, which is leftover stuff. So there is another stage where you move in your dirty pages also to the last step, which is like the last push. You put in them like to abhi bhag, and then you turn off the VM in your source destination. Now, this is the first capability, and at good enterprise levels today, there are things in place that can move hundreds of VMs within seconds. Okay, all without losing states. Even if I have seen this happen with HA proxy. I have moved HA proxy receiving like thousands of RPS from one server to another. Nobody noticed anything. Okay, this is a good use case.
What is the frequency of migration? Because you said it's an automatic. Okay. So I'm thinking two things here is what is the frequency of migration trigger, and another is the cost, because it's again shifting from VM to new VM, right?
Yes.
So it's a transfer of data. Then what will be the cost and the frequency, like how frequent it will happen?
Okay, so this is a good question. If you were running in traditional architectures, the cost would be very heavy. Okay, because you are moving only in compute related infrastructure, but your storage has to be rerouted now. Okay, so there is a traffic switch also. So not only the VM is shifting, your traffic also needs to be rerouted, so which is a bad thing. But in hyperconverged infrastructure, the good thing is because you've replicated metadata and data as well, the data of VM running, so VM A running on host A is also present on host B. So when the VM moves to host B, VM A moves to host B, it will read briefly from host A and then switch over and start reading from host B, because there is data locality of VM A in host B also. Okay, this is a good performance advantage. Okay, so this is what.
So the migration of VMs may not be only when some failure occurs. It could also be to save cost. Like for example, VMware does this.
Yes.
That if you have a cluster and if some nodes are underutilized, some nodes are overutilized, it does this balancing. And you can schedule that do this balancing in off-peak hours. So migration is not only to
Correct.
failover. It can actually lead to cost.
Yes. So that feature of what Saurabh is saying is called I think DRS.
DRS.
It's called DRS. Okay. So this is actually skew stabilization. So if you are running a 10 node cluster and somehow your workloads over time kept getting placed onto node ABC, for example, node 1 to 3 and 4 to 10 are relatively lower, you can schedule DRS to balance those VMs. Now, this is a good question. This is where vendor thought processes kick in. VMware thinks that if this queue is there, I should balance. That is their thought process, and they want to do that to reduce load per node. Okay, Nutanix does not think that way. You know why? Nutanix says resource hai uspe, chalega. They're like, what are the CPUs there for? To be utilized. Let us run them. What they do is so Nutanix is very tricky with this. What they do is they tell if one node, for example, let us think hypervisor A has the capacity to run 50 VMs, and you are running 48. Nutanix won't migrate those nodes until you hit 50 VMs per host. They will be like, it is there, so it will utilize. If it hits the bottleneck, I know what to do. Okay, so Nutanix in fact penalizes skew normalization. Okay, so it puts a weight on the VM that you migrated out to an empty host because it says that you interfered with my scheduling awareness. Because I knew this was loaded, I was running it. But what happens in enterprise, we also don't trust this decision. So what people do is they're like, I know you will put penalty, I will equalize for the sake of it. And the reason they do this is because if you're running 48 VMs, 2 more VMs came onto that node, right? The host will run out of memory or compute. So what that does, right? It triggers something called as a force restart of VMs. The VMs are all powered off, and then the scheduler kicks in again, and it works its algorithm of distributing the workload again. We want to avoid a restart, so they distribute it usually, which is a good point actually. Huh?
What will happen in the case of bare metals?
Bare metals is basically, they have their own logic. So if bare metal, the analogy would be running something vendor agnostic like KVM. Okay, it has its own VM migration. I've not worked with KVM, but I know that it supports live migration and all these DR scenarios.
Yeah, so I have a dumb question, like between the data migration, like is there a scope for the data to be corrupted or like some malicious code to be injected? What's the chances of that happening, and how do they handle this?
Got it. That's a good question. So because we are a distributed systems, there's a lot of metadata and data replication systems in place. Nutanix specifically uses Cassandra for metadata rebalance, and they have their own MapReduce framework for doing replication and all these distributions. So in the case of configuring a cluster, the administrators are given a choice. Depending on the criticality of the data and how much available you want it to be, you set something called as a replication factor per cluster. This is also a common term, different vendors use it with different names. Replication factors is the number of metadata components you want to be in place so that you want to recover. Okay, metadata number defines your fault tolerance. If you have I'm not able to recall the ratio, right? It is something like if you have 3 metadata copies, you can lose 2 nodes, n-1 kind of a relation of sorts. I can maybe revisit that. I don't know the ratio, but yeah, you get to configure how many replicas you want so that the rebuild is effective. Okay, if you have mission insensitive workloads, you're like, let it go. Like in dev environments and all, you can run it with just RF1. You can be like, chalega to chalega. But generally they run with RF2. And the reason for that is when I said replication uses copy on write technology. Okay, the more RFs you configure, the more reads and writes have to be acknowledged by the entire cluster before proceeding with the next set of operations. So that becomes costly. Okay, so we did run one cluster at RF3, which was our card data environment. Okay, so we ran our card data environments in Nutanix with RF3. The remaining all workloads were RF2, which means we were at RF2. We had the capacity to lose one node at a time. So that is one thing. So
One more question. You said that usually if a server or a hypervisor decides to migrate, then it will happen. And is there a copy of the VM like running as an active? Is it
No.
As active, passive, standby, stuff like that?
No. So what happens? The metadata of the VM is being actively replicated depending on your configuration. The data is being, there is a secondary copy of the data block sitting in another host, which is distributed actually. So in the time of a failure or a migration, you're in a capacity to build. This is a good question, and which is this slide is actually addressing. You're in a capacity to rebuild that. So if you see in this node, failure mode 1, as I told you, a lot of this is software defined, right? So the first virtual machine that gets created on such hypervisors is called the controller VM. Okay, so controller VM is mostly responsible for your things like scheduling, storage routing, interfaces, networking, OVS, everything sits in the controller virtual machine. This is the reason why we are getting performance. This is the reason why we are getting intelligent nodes. If this fails, right, before that fails, let us take a look at how the metadata distribution has been explained here. Node A had A, B, C, D fractions. Okay, A is sitting here, A is also sitting here. Okay, so we are in a RF2 category of sorts. B is here, B is also here, and where else is B? B is one part. Okay, so B is already there. C is of 2 occurrences, I believe.
Node 3.
Node 3. So there is at least one extra copy of this, and the logic here is, if node 1 fails, another node from 2 to 3 should be in a position to build ABCD securely with enough capacity. Okay, so if you see unavailable replicas, if the CVM goes offline, the storage routing and stuff, takes a big hit. You have lost access to reading those replicas. The VMs are no longer able to read the data they're writing into. But because this is a distributed system, another CVM here can say that, hey, you don't worry, I have data, I will route it to you temporarily. Okay, so there is a storage path failover that takes place internally at a software level. So this is called data path redundancy. Okay, so data path redundancy in hypervisors ensures that if data locality is lost, data is not lost. Okay, the path will change.
So, like, again, this is a dumb question, but what I wanted to ask is that in case of these storage-defined data centers where we are having abstraction storage this way, so are we running on something like RAID, or is it like are we running on something like RAID, or are we doing like again this is at software level? So is it like something we are doing something like consistent hashing key? This data block should go to this.
Yeah, it's mostly on that. But the thing is, on the hardware level, this is an equivalent of RAID 10.
RAID.
Okay, it's an equivalent of RAID 10, and because what we're doing is, striping across our metadata in a way where ability to rebuild is present always. And in RAID 10, what happens always, you have one node which is only meant for rebuild. Okay, which also means that if you have a cluster of 10 configured with such things, one node is exclusively at loss. You're not able, if you consider capacity wise, overall one node is actually wasted, but it's wasted for a good reason. It's a good problem to have. Okay, so
RAID 10, can you explain RAID 10 in a little more depth?
I think, correct me if I'm wrong, guys, I think RAID 10 is striping and what's the other one? Mirroring. Yeah, so
Combination of RAID 1 and RAID 2.
correct. So you are replicating data also, and you're like in bits and pieces correctly distributing it across available nodes. Yeah, and then there will be one node which holds the logic for this, how to rebuild. Okay, it maps the rebuild, this thing. So yeah, so everything. Okay, this is a fun part. In a lot of application level, people like say Elasticsearch. Right, people will be like, hey, I can configure my shards, I have shard replicas or whatnot, and then at SQL people have like read replicas and whatnot. But to an infrastructure guy, right, for me everything is data. I have to treat by principle everything as data blocks. Doesn't matter who is writing, because I have hundreds of VMs writing to me. One VM can be SQL, one VM can be Redis, whatnot. I don't care. For me, it is blocks of data. Okay, and to this reason, how hypervisors interact with storage is in data blocks. Okay, they start with blocks as small as, I believe, page level sizes of KB, either 4 KB or 4 MB something, and they scale in units of that. Okay, so I forgot the name actually. It starts with like say this, and then that becomes a block becomes like a LUN, and then LUNs are attached as further logical thing. The abstraction only keeps going up, but end of the day it is all smaller data blocks. Okay, so this is what it is. So your job is to govern and secure this data. And when I set RF and everything, I don't care what I am grouping, because the software is grouping it into logical reasons of making the entire cluster available. We are not doing application specific things here. So if you see failure mode 1, we got to know that if the brain fails, storage path can be rerouted. Failure mode 2, what if the node itself fails? Right, I had 10 VMs running on the node. node is gone, power supply trip, somebody did something, gone. Okay. The fun part is in RF2, I told you, right? If you have RF2, you have consistency to fail one at a time. What this means, if node 1 is completely lost, you know that its data and metadata are available in the another node. So as long as there is capacity in the remaining nodes that in the same cluster, the workload ABCD and its VMs can be effectively shifted. Okay, the load per node will increase obviously, but you are tolerant. This is called fault tolerance. Okay, the ability to lose a node and continue running. Okay, and what happens is when you lose a node, right, the storage controllers in other nodes actively acknowledge that. They're like, hey, I know my partner is down, I need to start immediately rebuilding data for him, so that the VMs that will come in, which is due to the forced restart, they have to be accessible for those partitions.
So when node fails, will the VMs be live? There is no live.
No, there is no live migration. That's a loss of VMs.
So as an application person who's spin up a VM, I'll see, oh, my VM got restarted.
Yes, that's what. The VMs will restart in the case of a node loss, and the VMs will be migrated in the case of a resource contention. Okay, so those are two differences. That's a good interview question actually. People ask, they're like, hey, tell me the difference between, what do you say, VM, when do VMs restart and when do VMs migrate? Tell me that. That's a good question. Then people have to define all this. So that's a good thing. So yeah, but the dirty little secret here is when I say I lose one node, I rebuild, right? Rebuild takes a performance penalty on the cluster. If you are observing your systems during rebuild, you will see things spiking a lot. Writes are spiking a lot because there is a rebuild taking place. But the good thing is, once rebuild is complete, the metadata redistributes itself. You're again fault tolerant. So you're again in RF2, which means you're again in a position to lose another node. Okay? And you can continuously keep losing nodes until you actually hit a physical capacity constraint.
Which is where the over provisioning and headroom.
Yes, right. So this is where all of that needs to be factored in. So I can fail until I actually cannot. So this is your dirty little secret. People always run with over provisioning because data center operations are a privilege, right? You still have to leverage it with intelligence, because you can't tell business that, hey, I am factoring 30% for failure, so please order 25 more servers for me. They'll be like, pagal hai kya? So we cannot do this. So we try to do that with data driven inputs, saying that this was consumption, so effectively this should be my headroom.
In your practical experience, what have you seen? What's the utilization of the data and the servers overall? Is it people run it at like 50% would be considered a normal thing, or like 70 would be a...
It actually, the good thing about this is it depends on the core engineering team who are brains behind it and their biases, from my experience. Okay, my organization ran at 60% utilization, 40% headroom. Okay, but there are some people who run below 50 and say that they like to boast that we have 2x capacity. They're like, your traffic doubles also will handle. So it actually, it's a depending on the mindset of the engineering teams that are core responsible for it, So it's a thing, comes from bias. Then actually teams have to evolve into that. You have to work backwards. You have to work with the data you have to work with utilization patterns, because obviously at some point the organization will get into a cost cutting exercise. And this is where engineering managers like to crunch numbers and be like, hey, we are running so much extra, we can cut this down. Things like that.
Okay, but may do like provisioning teams kind of take into account that, hey, if I do need to order more servers, more hardware, well, some kind of extraneous event, like some kind of say problem with Taiwan and all,
Mhm.
lot of hardware will come from there. So if there's a chance that for next 6 months the availability of new hardware might be impacted. So instead of ordering new stuff at 70%, maybe somebody can start ordering at 50% itself.
Yes.
And then what do you do in case you find yourself with extra hardware and less?
Good question. This is actually a thing called, remember I told you guys how to look at a data center, NCS. What was the fourth one? Power and auxiliaries. Auxiliaries are your stock kits. Okay, per data center, I ran 5, our team ran 5 data centers. So the per data center stock there kept was 10 servers. Okay, 10 per thing is either for spare parts exchange or it was for direct capacity addition. But this is a good thing. The one way companies address this is pay as you go model. Okay, they are doing this. Dell can provide you extra hardware in advance, which is something an equivalent of reserved or reserved instances. They'll give it to you in delivery. If you don't use it, you don't have to pay for it. But if you need it, you have access to X number of servers sitting in your warehouse. You had a question? This industry over provisioning is great. You should be running. Failure mode 3 is the ultimate failure mode. Your cluster itself is gone. Okay, so this is where things get interesting. Okay, so you can see this is your site 1, for example. You are running your local DSF. DSF is a distributed storage fabric. Okay, let us call that as if I have 10 nodes and I had storage from 10 nodes, there is a storage fabric running across that, which is the equivalent of Ceph, for example. It's running across node distributed storage. You have distributed storage, and then you have a data store running on this. Data store is something for your virtual storage blocks, like the storage attached per VM, for example. All of those are being served in blocks here. Your VMs are interfaced with your hypervisors doing IO operations with that. This is your site 1. Things are looking good. But because you're a good engineer, you have configured data and disaster recovery. Okay, so what you have done, as we told, we are a private cloud operator, and we are also IaaS providers now. Good IaaS providers have disaster recovery sites. So you approach site 2, which is a replica of that site. And this is where again cost comes in. Many companies choose to run this in live so that there is at least business value in running another site. It makes no sense keeping an empty site waiting for a disaster because you are paying. And the reason you have to pay equivalent as running a production site, because the day you fail over, the equal amount of resources are going to fail over. So people tend to run this in active so that things are good, like justified of sorts, also for good reasons, of course. So
Traffic split across.
Yes. The same network is being made available across 2 data centers with concepts like VXLAN or stretched networks, and then both of them are serving production traffic.
And then that means even more over provisioning.
Even more over provisioning?
If you are running more than 55% on each of them, then if one entire
Yes.
Some VMs will not be obviously able to.
So this is to cater for service degradation. So this is actually the difference between making your business completely unavailable and or being degraded. You would prefer to be degraded than being unavailable.
So when you site 1 and site 2, are different racks or
different data centers. Different data centers. So this actually, when we different data centers for this.
This is done basically majorly for natural disaster management. Let's say
Could be anything. Power trips also. The fun fact is, in my previous organization, we were migrating a data center, and there was a power outage because the municipality team in London dug up a pipeline and cut off some power cables, and our entire zone lost a power. Like one data center lost a power. Good thing we were in the middle of the migration, so we had 2 extra data centers as co-location, and they were already networked. But God forbid if they were not, you will lose a zone. So for these things, what happens? You create a stretched network. Okay, implement VXLANs, and as I told, we are not going to implementations. What they do is do 3 types of things. You can establish 3 types of replications here. So if you guys have heard of snapshots technologies, right? VMs are snapshotable. So what? Snapshots can be restored anywhere. I can send that snapshot file to you in Teams, and you can set it up in your things like that. What they do is 3 base, depending on the size of your organization, capacity and capability of your organization. There are different kind of network benchmarks that you run on. Okay, some big providers like Amazon can flex that my inter-region latencies are sub 5 ms. But if I am a regular day corporate who runs data centers, I can just say that, hey, my 50-second latency is there, 50 millisecond latency between data centers. Depends on business. So depending on that, these providers offer 3 types of replication opportunities for you. First is called asynchronous, where you set something called as a RPO, recovery point objective, okay, which defines your RTO, recovery time objective, time to recover your VMs. So the least they start is from minute level, depending on the bandwidth you have, because you need a high bandwidth to transfer those snapshots to site. Usually people keep it at 30 minutes. So when you keep it at 30 minutes, what is it? It's the business accepting that I am okay with the state being restored 30 minutes older than what it was. Okay, so this is what replication means. You can do this asynchronously. Transfer snapshots, keep dumping it into this data store. Okay, so here VMs are not running, but data stores are running. But on the day when you lose, VMs will be created, snapshots will be attached, traffic comes up. This thing is fully cut off, right? So this, each site is independently running its own Nutanix cluster basically, and then each site has an active copy of the other site's data store, right? So now let us fail the network. So site 1 is gone, right? So as we discussed, site 2 is completely capable of taking over operations of site 1. For this reasons, people over provision, and what also happens when these things come up, right? There is a tendency of near 100% consumption of bandwidth. Okay, because not only the VM is failing over and they are coming up, the traffic is being rerouted. So your bandwidth, even I have seen bandwidths, 100 gigabit bandwidths, InfiniBand between two data centers being choked. Okay, they are like nahi ho raha hai. And then we had to keep another separate graph which was showing bandwidth in GBPS, saying that keep it under this, and we had to do it in night time when the consumption between that was very low, right? So in this case you can see how site 1 takes over this. So asynchronously is for those businesses who cannot afford top of the line equipment. They're like, it's fine if I lose 30 minutes data. Synchronous replication is a good option for businesses running top of the line equipment, and this is usually what say maybe trading companies use. Trading companies, sports companies who rely on real-time stuff. I don't want 30-minute old data. Okay, I want now. Those guys use something called synchronous replication. Immediately, writes are sent. Now, when it reaches is dependent, is a function of the latency on the network point in time, but it is immediately sent. It does not wait for 30 minutes. So the snapshot is continuously receiving things. So this is like a concept of VM live migration happening across data centers. Okay, the capability this brings to you is you have immediate recoverability, near zero recovery time, or you have lost only seconds of kind of data. The best case is AWS level things. Those are called metro availability. Metro is when you have guaranteed sub 15 or sub 5 millisecond latencies between your data centers, you are in a position to instantly restore. That is the equivalent of clicking in the same cluster. If I do migrate VM, right, how fast it happens. That capability is there inter data center, because your network capability is guaranteeing that. And the one main constraint why people can't do that is they don't guarantee inter data center connectivities to be less than 5 or 15 ms, one of them. So yeah, this is, I think, a failure mode. I think as if things bigger than data center fails, I think you have bigger things to worry about other than business. So better to stop the failure modes at here. You've lost a disk, you've lost a node, you've lost a data center. We've catered for that. Good job, well done at the day. If something bigger than that fails, I think come back to home. So yeah, I think
In case of replication, you're talking about this is an active replication.
Mm-hmm.
So that's fine. You're talking about a data center level, but also considering the application level. So let's say if I'm running a stateful system, right? It has a data store being used in one data center. You're telling me that we are actively replicating it. You showed that in the diagram in the previous page, right?
Mm-hmm.
That there is one data store and there is a copy of that data store in
Yes.
another data center for the same thing. So it seems like there is a bidirectional.
Yes,
right?
yes.
But then how does the application is aware of this? Because if I'm running an application which is a stateful application, which has a database, my database is not like aware of you are doing this application. So how does it handle that? Because
Yeah.
database needs to be configured for this thing.
Correct. So actually, this is an implementation level detailed question. It's also been a while since I've not touched it, but I can give you 2 pointers on this. So they implement 2 technologies called as rack awareness and application awareness. Okay, this is actually some form of matching the execution context currently in that point in time that your application, can be anything, is interacting with, along with the status of how much metadata has been distributed for that to be able to recover in point in time. Okay, so I can maybe point you to links to that, but I cannot have a explained answer for that.
This active replication is not just a decision the data center operator can take.
Oh yes,
Because then my application needs to be aware of this.
definitely. This is a good point actually. So the day that it failed, right, we were ready for a failover. We had this sync replication happening, and how you fail over is with a click of a button. Okay, you say that site 1 available, move. But that day the 2 teams said we cannot authorize you for that. The first team was MS Exchange, I think. They said no, we are not at one point. The other team was some very stateful team only. I think they had some application running and they said that we are not in a position to guarantee no data loss despite you having replicated to us. And actually this is a curse on us, because as I told you, as infrastructure engineers, we treat data as data. because I'm running 100 different people's data. So I cannot cater to one specific fella, and this is primarily the reason why we actually do this. Remember I told you, given a data center, why do you categorize? When I put people in general purpose cluster, I am giving them as a cloud provider my guarantee that you are somebody who is accepting a contract with me, that it's okay for you to fail momentarily. It's okay for you to take hits in certain network compute storage overheads momentarily. The guys who are very compute or storage sensitive, we create different kind of network and availability patterns for them actually. So this at this point it gets into architecture and principal level knowledge, so where they propose custom bespoke solutions for them. So we had a case where Oracle was running on bare metal, they wanted to come into Nutanix. There was a case where HA proxy was running on bare metal, but they wanted to come on Nutanix, and at some point they figured out that they couldn't, because HA proxy does some sort of heartbeat checks, right, when it runs in a group. That heartbeat signature was not being guaranteed by how frequently our hypervisor cluster nodes check each other. So they said no, like I will find out too late if this failover takes place. So all of that, they said there are cases where candidates for virtualization should be picked correctly actually, and this is the reason why people in private clouds run a multitude. People say, "Arey, tum legacy infrastructure chala rahe ho." Sometimes it's actually not possible to move into virtualized platforms. Okay, this is a real use case which ends up which is a function of business being stern about it, technological limitations like this, and so people as engineers we have to it is our job to correctly tell people that hey, your application is fit being virtualized or not. Okay, sometimes you're better off running on bare metal, leave it, no, go for it. So yeah, this is actually some things, but yeah, I think hopefully this was it. We've failed over till a data center and my talk ends here. We're open for questions.
In the case of data center failure, what will happen to the sticky sessions? Sticky sessions.
Yeah, data center level failures are actually outage scenarios. So you will lose. You will be degraded. So whoever was in that sticky session level categories, they will lose. You have to re-establish and like put up a status page. This zone is gone, whatever. We are coming up shortly, or saying that X% of traffic is being routed here, whatnot. That is an outage scenario proper. At that point, we are not in a position to hold on or maintain state, loss of state.
Mentioned that when we actually do a failover and like try to bring up the other data centers, so there's like I don't know, some companies might provide like RP of 30 minutes, like 2 minutes, and you mentioned that it's a function of the latency that the network offers you. How is it a function of latency and not a function of bandwidth?
It is of the bandwidth. No, so the thing is, for example, if the application is a very small function, right, it's not taking on heavy storage, heavy chunks of storage, migrating that is not an effort. Okay, migrating in time is the effort. So you have to be time sensitive there. It might be a very smallest of a small application, but business demands that I cannot afford a loss of 30 minutes for this. I want it immediately. So your network should be in a position, obviously it's a function of, like say, bandwidth comes in where if the bandwidth is free, you can move this thing, but you need latencies to be a major factor here, actually.
How?
Huh?
How?
It's because the time taken to transfer your snapshot across from point A to point B matters more than your size. Then the given underlying assumption here is data center to data center connections are anyway mega bandwidths.
Right. So ideally, if you can parallelize your data copy enough, if you can, so going back to your blocks, copying blocks analogy, right? So if you can actually read it, say 16 MB blocks or whatever, and then start like pumping them in parallel, you can overcome the latency, right? You can just cut the pipe.
Yeah, but at least from what I have seen, these are actually very like deep tech. Say like the implementation of such things are a deep tech offerings by the OEM itself. We have only option to select this. They can say that this is your state. The options are present to you automatically.
Yeah, just the point I want to make is RPUs are almost always a function of bandwidth. They're not a function of latency. You could have very low latency and very constricted bandwidth. You will have bad RPU, right? You could have
Right.
like high latencies but high bandwidth.
It'll make it work.
your RPU can be still good.
Okay, I think the major, like one maybe where I'd have to look back on is underlying assumption of being bandwidths being big during inter data center is one reason the focus they put is on latencies. Like the documents they mentioned, right? Usually the only focus is on latency. But yeah, I think we can definitely discuss that on how it's catered.
So from an application point of view, we think of applications as either stateful or stateless. Right? So let's say if I'm running a simple REST API, then it's typically a stateless application. It could be a container or I could be running it on a VM, doesn't matter. Then there is databases like I think Sitaram was mentioning that I'm running Elasticsearch or Postgres, Redis, whatever. It could be in a single VM or a container or it could be a cluster in itself. But is it fair to say that from a infrastructure, data center management infrastructure point of view, each VM is anyway stateful? Because that VM has memory.
Yeah, we are seeing state as in terms of memory.
Correct.
Huh.
VM has memory, that VM has disk, and
Yes.
it could also be talking to other VMs as a cluster that you don't even know if that's happening. So ultimately, all of it becomes stateful in nature.
Yeah, the cluster level that met the state, as I told you, Cassandra maintaining all of this it's a combination of cluster state being maintained by metadata on what is going on per entity there. So metadata is tracked in terms of entity. VM is an entity, storage block is an entity, a network VLAN is an entity for the cluster. So it tracks all that. Then there is actually a sideline implementation of Zookeeper, which tracks metadata of configuration per entity. If there was a VM, how did it exist? What disk it had? What are the ideas? All of that is maintained in Zookeeper. So there is a question of quorum and metadata that needs to be balanced when this comes across. So yeah, the cluster in itself is a stateful thing, right? Because it's a mega distributed system. So, but yeah, I think it's a good thing. But I think one thing I can admit is most of these things are already given to you in an implemented state. Okay, so the way you gain knowledge is by reading up their user manuals or if you play with their technology. But to be able to implement these things for yourself, for example, like Nutanix uses Paxos for consensus, and then they use this inverse knapsack for workload placements. All of this is that can come to you if you read their research papers. They have published with universities on how they did all of this. So you would have to go down to that level if you want to implement. But most of the infrastructure engineers at that layer are mostly consumers of this knowledge. So yeah, thank you guys. This was the talk. Sure. We can read out this. No worries. Thank you. Ishan, we can move in, right? Cool. So also one plug is come talk to us for one-to-one carriers. We are hiring. We have got Chinmay and Pradna, right? So we're good to go. Cool. Thank you.